Here's another example of changing variables. The previous example which we did with the r and theta, the change of variables itself, the r theta business, is rather generic. It's something you do all the time, changing to polar coordinates. And therefore, it's good to remember that the Jacobian is r, and it's very useful. In this example, it's going to be something more local. So it's going to be a change of variables, which is really kind of the whole example is set up for a specific change of variables, which is not necessarily ever going to be used again. But the idea is nevertheless important. So suppose we want to calculate the double integral over the domain D of the function root of x, y, dx, dy. And again, I have to tell you what D is, of course, where D is bounded between the parabolas y squared equals 3x and y squared equals 6x, and the hyperbolas y equals 4 over x and y equals 9 over x, for x and y non-negative. So in the first quadrant. So let's understand what this domain is. So these are obviously parabolas, but they're parabolas where x equals y squared up to a factor rather than y equals x squared, right? So they're parabolas that look like this. Do you agree? Okay. And these are hyperbolas. These are just modifications of y equals 1 over x, scalar multiples of y equals 1 over x. So we know what those look like. So let's draw the domain. So we're in the first quadrant, so I'm only going to draw the first quadrant. So we have y squared equals 3x and y squared equals 6x. So those are two parabolas that look something like this. Well, I need more space. So those are two parabolas that look something like this, maybe. So this is going to be y squared equals 6x, and this is going to be y squared equals 3x, right? They continue down here, but I'm only interested in x's and y's, which are non-negative. So I'm up in the first quadrant. How do I know which one is which? Which one is the wider and which one is the narrower? You're mumbling. Can't hear you. Okay, so at least for me, it's easier to think x equals y squared rather than, y equals x squared. So if I would think of it as just to think, just to understand. So obviously, if I were looking at x squared equals 6y and x squared equals 3y, those were their more user-friendly, at least when I'm the user, parabolas. I could rewrite them as y equals x squared over 6 and y equals x squared over 3, right? And when I divide, I take y equals x squared. When I divide by 3 at each point, I'm making it, so if this is y equals x squared, then y equals x squared divided by 3 would make it somewhat flatter, because at each point I'm dividing the value by 3, right? And when I'm dividing by 6, it would make it even. So this is x squared divided by 3, and this is x squared divided by 6. Do you agree? Okay. So likewise here. Okay, so this was just a side remark. How do I recognize which is which? Okay, And now I have two hyperbolas. So these are the hyperbolas, tell me if you understand what I'm doing, that look like this. That's 1 over x up to a scalar multiple. So when I look just at their positive part, one is going to look like this, and the other is going to look something like this. Right? They both have the axes as asymptotes. Both axes as asymptotes. Do you agree? Okay. And y equals 4 over x is going to be the bottom one. Right? I'm multiplying by 4, whereas here I'm multiplying by 9, the 1 over x. Do you agree? Okay. So what's our domain? Our domain is this thing, this region here. This is D. Do you agree? Once again, D is a simple domain. In fact, it's simple rather whether you choose it in this direction or whether you choose it in this direction. It's always a simple domain. Nevertheless, to calculate the integral, again, would have to force us to break it into 3 domains from here to find all the intersection points, and then from, let's say, from here to here, and from here to here, and from here to here. And can you see that it's going to get a bit messy? Okay? But this domain kind of talks to me, okay? I look at it and we communicate, and it tells me, hey, why don't you define new variables as follows? And so define new variables, we're going to call them u and v, in the following way. I'm going to define y squared to be u times x, and y to be v over x. Okay, so this defines new variables, u and v. This defines new variables, u and v, where, so u is y squared divided by x, and v is xy. Do you agree it defines new variables in terms of the old variables? Right? And in these new variables, what's the new domain going to be? That's the reason for choosing these new variables. D is going, or D maps to, is rather not formal. D maps to E, which is a rectangle. Points in D satisfy that the u's are between 3 and 6. They lie between y squared equals 3x and y squared equals 6x. So u is between 3 and 6. And v is between 4 and 9. They lie between y equals 4 over x and y equals 9 over x. Do you agree? So this is a rather ad hoc substitution. It's tailored for this example, tailored in the Butler sense and not in the mathematician sense. Tailored for this example, nevertheless, it's kind of a good thing to try. Do you agree? Okay. So if you want to use this substitution, do you agree that it's a good idea to try, because we get again an integral over a rectangle? Do you agree that the domain transfers to this rectangle in a one-to-one way? Each point here corresponds to exactly one point in this rectangle, right? You can't have 2 points which are going to map to the same point here, okay? So the only thing that remains to do is and what is the function? So the function we had, f of xy, was the root of x times y. So what's the function going to transfer to? It's just going to be the root of v, right? Because v is x times y, so the new function is going to be the root of v, right? xy is just v. Okay? So the only thing remaining is to calculate the Jacobian, right? Okay, so we have to do that. So let's do that. And calculating the Jacobian sometimes requires some work. So let's do that. Now, before we calculate the Jacobian, there's one thing to point out. Here we wrote u as a function of x and y, and v as a function of x and y. But that's not what we need to calculate the Jacobian. We need to write y and x as functions of u and v, right? And then take the derivatives of those with respect to u and v, and plug them into a determinant and calculate it, right? So we first have to kind of find what x is in terms of u and v and what y is in terms of u and v. So that's a bit of fiddling around. Let's do it. So remember that y is v over x, therefore x is v over y, and y squared is u times x, therefore I'm going to plug in, instead of x, I'm going to put v over y. So y squared equals u times v over y. Do you agree? So this is the reason for this. And therefore I get that y cubed is u times v, and therefore y is u to the power 1/3 v to the power 1/3. Does everybody agree? And once I have this, I can find x. X is v over y, we agreed. And y is that thing, so we have v over u to the power 1/3 v to the power 1/3. And therefore, x equals u to the minus 1/3 times v to the 2/3. Good? So this is x and y written as functions of u and v. That's what we need in order to calculate the Jacobian. Good? Now it's just a matter of calculating some partials. So the Jacobian, which is dxy to duv, is what? Is the determinant of the derivative of x with respect to u. Okay, so the derivative of x with, bless you, the derivative of x with respect to u is, it's u to the minus 1/3. So it's minus 1/3 u to the minus 4/3, right? So it's minus 1/3 u to the minus 4/3, and then there's this v to the power 2/3, which is just a constant when I'm doing partial with respect to u, right? Okay, the derivative of x with respect to v is 2/3 v, well, let's write the u first. U to the minus 1/3 v to the minus 1/3. Stop me if you disagree on anything, okay? Now the derivatives of y. With respect to u, I get 1/3 u to the minus 2/3 v to the 1/3. And the derivative of y with respect to v is 1/3 u to the 1/3 v to the minus 2/3. A bit nasty, but not that bad, right? And in fact, it's going to simplify greatly when we do the determinant now. So I have this times this. There's a minus 1/9 there. Minus 1/9. And what do I get? U to the minus 4/3 times u to the 1/3 is u to the minus 1. And v to the 2/3 times v to the minus 2/3 is just 1. Do you agree? V to the minus 2/3 times v to the 2/3 is just 1. Right? So I get u to the minus 1 minus 2/3 times 1/3 is 2 over 9. So minus 2 over 9. And then u to the minus 2/3 times u to the minus 1/3 is u to the minus 1 again. And v to the 1/3 times v to the minus 1/3 is 1. So again, I get u to the minus 1. So minus 1/9 minus 2/9 is minus 3/9, which is minus 1/3 minus 1/3, and then u to the minus 1 is just 1 over u. So it's minus 1 over 3u. That's the Jacobian. Good? Did everybody follow? Okay. So now let's calculate the integral. Let's go back to our original integral, and remember, this was our j. Okay, and also remember that it took a bit of work. Okay, finding j sometimes hides a bit of getting your hands dirty. Okay, so minus 1 over 3u. So let's go back to calculate our integral. Let's go on this board. So we want the integral, the double integral, over the domain D of root xy dx dy equals, the domain E is now a rectangle. So I have the integral from 3 to 6 du of the integral from 4 to 9 dv. And inside I have root of xy. Xy is just v, so it's root v. And what do I have to multiply it by? The Jacobian in absolute value. So the Jacobian was negative 1 over 3u, so in absolute value it's just 1 over 3u. This is the integral I now have to calculate. Good? I urge you to try and calculate this without changing variables. Using just iterated integrals for simple domains. You're going to have to figure out all these intersection points and break it into simple, nice domains like this. There's going to be this, and there's going to be this, and it's going to break into three separate domains, and you're going to have to find all these points and try it. See if this is worth the effort. Okay, from my experience, it is, but you should try it for yourselves to be convinced. And moreover, I'm going to show you in a few, after we solve this, I'm going to show you a shortcut to calculating the Jacobian. There is a shortcut. Okay, so let's calculate this integral. So what do we get? I can already see that I'm not going to have enough space on this board. Okay, but let's start. So it's the integral from 3 to 6 du of, here we're doing an integral dv, so we want to find the antiderivative of v to the power 1/2. What's the antiderivative of v to the power 1/2? It's v to the power 3/2, right? But then we have to multiply by 2/3 in order to cancel the coefficient. Do you agree? Okay. And then all of this we have to calculate between v equals 4 and v equals 9. And then there's that 1 over 3u, which doesn't even see that integral dv. And all of this we have to integrate du, right? These steps should be steps that you take carefully in order not to make mistakes, especially when you substitute values. Make sure you substitute them in the right places. But these should be steps that you feel the relaxation of being Calc 1-ish again. Okay, this is stuff you know from Calc 1. Okay, so what do we get? The 2/3 here and the 1/3 here give us 2 over 9, which is a constant I can pull all the way out of this snake. And then I get the integral from 3 to 6, 1 over u. And what do I get here when I plug in the values? When I plug in 9 for v, to the power 1/2 is root. So it's root 9, which is 3 to the power 3, which is 27. In fact, I can pull that out of the snake as well. So 27 minus, when I plug in 4, root 4 is 2, 2 to the power 3 is 8, and that's it. And now I can write the integral. 3 to 6 du over u. Good? So what do I get? 27 minus 8 is 19. 19 times 2 is 38. So I get 38 over 9. It almost fits on this board. Oh, fine. Let's move it to the other board. So it's going to be, what did we see? 19, 38. 38 over 9. What's the antiderivative of 1 over u? ln of u, right? U is positive here, so we don't need the absolute value. So we're going to get, let's continue here, equals 38 over 9. And then we had ln of u evaluated between 3 and 6. Good? So we get 38 over 9, ln of 6 minus ln of 3. The difference of logarithms is the logarithm of the quotient, so it's the logarithm of 6 over 3, which happens to be 2. So the final answer here is 38 ln of 2 divided by 9. Questions so far? Good? Okay. So what I want to discuss briefly is a shortcut for finding j in this example. So when we started out, when we first decided on the substitution that we're going to use, on the change of variables, we easily expressed u and v as functions of x and y. Okay? Whereas in order to express x and y as functions of u and v, we had to work a bit more, and even after that, it turned out to be a bit unpleasant, right? All these negative 1/3 and negative 4 over 3 and all these kind of annoying powers that turned out there, right? But let's do something different. Let's calculate the Jacobian of u and v with respect to x and y. Okay, let's do that. So I'm going to look at this board again. So remember that this is what we had when we did it the straightforward way, right? This is what we got. So let's erase all this. Well, I'm going to leave parts of it. I'm going to leave the calculation at first. And let's do it a bit differently. Let's calculate the Jacobian for the map going the other way. duv to dxy. And this Jacobian of the map going the other way, the inverse map, instead of writing xy as functions of u and v, writing uv as functions of x and y, this has a notation. It's called J inverse. The Jacobian for the map going the other way. That's what it's called, j to the power minus 1. So what is it going to be? It's going to be the determinant of u with respect to x, u with respect to y, v with respect to x, and v with respect to y. Right? Let's calculate that. I'll write here so we recall, because it's on a different board, that the functions were v was just xy, and u was y squared over x. Much easier to take derivatives of these, right? So what do we get? U with respect to x is, this is 1 over x, the derivative is negative 1 over x squared, times this y squared. So negative y squared over x squared. Do you agree? U with respect to y is 2y over x. V with respect to x is y, and v with respect to y is x. Good? Now let's calculate the determinant equals. So what do we have here? We have minus the x and the x squared cancel, so we have minus y squared over x, minus y squared over x, and minus from this 2y squared over x. So minus y squared over x minus 2y squared over x is minus 3y squared over x, and y squared over x was u. So it's just minus 3u. Good? And obviously this was much easier to calculate than first transferring everything what I erased here and then calculate this rather nasty thing. Right? And what did we get? The Jacobian corresponding to the inverse map is 1 over the Jacobian corresponding to the original map. Okay? And that's a theorem. It's not a coincidence. J inverse is in fact 1 over J, always, and that's why it's denoted J inverse. Okay? So, let me write it here. Theorem. I'm not going to prove this, but nevertheless state it. J inverse equals 1 over J, and that's always true. Okay? The Jacobian of uv with respect to xy is 1 over the Jacobian of xy with respect to uv. Good? So in this example, had we known this in advance, we could have just did this calculation and then just remember to take the reciprocal, and of course when we plug it in we need the absolute value. Good? Everybody? Questions? No questions? Okay. So this wraps up this example, which was rather special, right? It was a change of variables which was tailored for a specific example, but this is an important consequence to keep in mind. In the next clip, I want to discuss the theorem that we're using all along. This theorem, I want to discuss some theoretical aspects. So for example, it's going to take a couple more clips. What is this J? Where did it come from? Okay, so we kind of said, okay, it's going to have to be some derivative trying to mimic what happened in one variable, and we said, okay, it's this. Huh? Why? Okay, why is this a good guess, and why is it true? And I want to discuss a bit these requirements of the theorem. Why do we require J to be non-zero? Why do we require the map to be 1-to-1? How do these relate? Could there be a map where the map is 1-to-1, but still the Jacobian is 0? Or could there be a map where the Jacobian is never 0, but still the map is not 1-to-1? Okay, how do these relate? All of that coming up next.